Hi, I'm Donna Ellis Wilson. Welcome to the Data Platform Women in Tech Data Science Beginners Day. This session is cross-apply psychology over the AI and machine learning fundamentals. And so the reason I chose this title is because we're going to look at the fundamentals of AI and machine learning through the lens of psychology and what psychology can teach. Machine learning and artificial intelligence, and how to be better data scientists in general. So first, thank you to all the sponsors: SQL Skills, Paper Sword, Redgate, SQL. What is this? Our SQL user groups. Is that what this is?
Yeah, that's Microsoft sponsoring all the user groups. That's what that is. Ree's supposed to get me a better icon at some point. So
that new icon.
Yeah.
It keeps updating, I guess. And DCAC, which is Denny Cherry, is that right? And Associates.
That is correct.
Session Eyes is powering this event today. So thank you to all of our sponsors, and thank you for all of the attendees who have taken time out of their day, whether it's their lunch hour or end of day, beginning of day. I appreciate it. This is a not specifically technical topic, although I hope you do find it more technical than you had anticipated. A little bit about me. My name is Donna Ellis Wilson. I am a data professional, and I have been since 1999. I have been in technology since 1994. I refer to myself as a data hat rack because I've worn a lot of hats in the data professional field. For about a decade, I was a support engineer at Microsoft. I've been a database administrator, again, for at least 12 years. I did that. During that time and overlapping times, I've been a data engineer, data modeler, database developer, and a BI data analyst. I am currently, as of today, unemployed, but that will change on Monday. So I haven't put in a current role because I don't currently have a role. I also have about 16 years of management experience and a BS in psychology. So for those of you not in the US, a BS is a Bachelor of Science, but also I felt like it was appropriate to call it the BS of psychology. So here's our agenda. We're going to cover what we won't cover. I'm going to introduce you to why I chose psychology to talk about data science and view data science through the lens of psychology. We're going to talk about psychology research methods and best practices. We're going to very briefly touch on emotion. We're going to talk about perception, memory, learning, motivation, cognition, metacognition, prediction, cognitive biases, ethics, and then I have a bunch of resources at the end. I did try to cite my sources as much as possible, and there were a couple scenarios where, well, there was one scenario where I did borrow an image from one of the textbooks that was so great, I just couldn't not borrow it. So big thanks to Goldstein for that lending of the image. So today we are not going to cover a deep dive into ethics of artificial intelligence and machine learning. We're not going to talk about the biases within that. We're not going to talk about data gathering, ethical ramifications, all of that. We're going to skip all of it. We're not going to do any deep dives into machine learning algorithms or natural language processing, prediction models, any of that. We're not going to really touch on abnormal psychology at all. We're not going to talk about Skynet or the coming robot wars. And we are definitely not going to talk about how you feel about your childhood. So why are we talking about psychology at all today? Well, first of all, it's something I'm very passionate about. I did just get my bachelor's degree, which for non-US people is a 4-year degree in psychology. And as I was going through the courses, several courses really stuck out as really being applicable to what we do on a daily basis as data professionals. In particular, when we talk about intelligence and learning and how it applies for humans, that really informs how we behave and how we make decisions towards data science. And so I really want to focus kind of on that aspect of it. So a lot of what I've cherry picked from psychology areas of focus and theory are related to intelligence and learning. So when you look at the entire field of psychology, there's just so much, and I only am hitting the tip of the iceberg. So definitely keep exploring, but not all of it really applies to us in what we're talking about. Psychology is actually a social science and has rigorous research methodologies. And in addition to that, it's a licensed profession. So there's ethical requirements and expectations of any licensed professional in psychology. We use data science both to predict human behavior and also to modify human behavior. So knowing about human behavior actually makes us better data scientists in general. And then we have a lot of iterative practices in psychological research that mimic data science iterative development, agile philosophies, and that kind of continuous improvement. So we can learn a lot from not only how psychology embraces a theory, evaluates it, and then lets it go. Think of Freud and a lot of his theories. They had a very large hold on the psychological community for many, many, many decades. And now almost all of his theories have been debunked, basically, and are pretty much, just taught for historical reference now. So the last aspect of it is that in psychology, you have basically feuding theories or conflicting theories. So you might have a certain behavior or a certain phenomenon, and different psychological researchers will develop theories to explain or test or somehow modify or create an intervention for that behavior, and it creates a very heated debate. And that debate is actually good. It's a good process that the scientific method instills in the social science. So it's very similar to a lot of the schools of thought and theories that we have in data science that really can generate a great deal of debate as well. Any questions so far?
That we can see.
Okay, awesome. So first thing I'm going to do is dive into the research methodologies. So and I'm going to try to cite everybody that I learned from, because I learned from other people, and I'll talk about that in the learning aspect of this. But in the book Psychology, Myers says we need to bring a scientific attitude. We need to bring a scientific attitude to data science, and that is the science aspect of it. One of the things that psychology does very, very well is measuring the unmeasurable. I didn't use immeasurable there because it's not immeasurable, it's unmeasurable. Psychology gives us this, this term called a hypothetical construct. And hypothetical constructs are actually used a lot in data science. You may not know them as that, but they are. So a really good example is intelligence. Intelligence is a hypothetical construct. And we cannot measure intelligence unless we measure an observable behavior of intelligence, such as how fast somebody finishes a story, the reading comprehension that they have after reading a story, their speed at deducing math problems, those kinds of things. And when we talk about those measurable aspects, those are what we call operational definitions. So the operational definition both measures it and explains how we are instantiating that construct. So another example might be resilience. Like, how do you measure somebody's resilience? It's not really something you can say, well, she's a 5 on resilience. What are we measuring? Like, how do we quantify something as intangible as that? And so really, when we are looking at these things, it is because we are trying to ask questions and test for those questions and then develop conclusions, to draw conclusions on it in the scientific method. And hopefully everybody here is familiar with the scientific method, but it's a process by which we make repeatable observations and experiments in science. So measuring the unmeasurable, there's a whole area of psychology called quantitative psychology, which I find fascinating. And it has a lot of overlap with data science because of how statistical it is. It has a lot of emphasis on testing, in particular, tests such as IQ tests or the SATs, or maybe tests for depression, tests for developmental disabilities or different abilities. All of those things really come to us from quantitative psychology, which is just such a fascinating area of psychology if anybody wants to investigate that. There are so many applications of just what I've discussed here, but within the research methodologies, we also have the concepts of the independent variable and the dependent variable, and lots of other tests within, such as construct validity. Construct validity refers to if I define resilience as somebody's wearing green socks on Thursday, I need to be able to prove that that actually aligns with previous research that has other operational definitions. So where you might draw parallels between data science would be, what makes somebody want to buy? Like, what is an incentive for a consumer? How do we judge their motivation? How do we, even quantify sentiment? What does sentiment mean when we start looking at it? And we'll come back to sentiment analysis as far as natural language processing a couple times, because it's a very good example. So any questions on that before I go? And we'll stay on research methodologies for a second here. I don't see any questions. Okay. So really, when you get down to the testing aspect of psychological research, it's all about determining causation. And when you have causation and correlation, one of the things that is a concern is this concept called directionality. And so in data science, there are a lot of concerns about correlation versus causation, as well as directionality, and understanding how variables affect each other, and the combination of variables and how they affect each other, and pulling those predictive kind of unknowns out of data that already exists. Those are both aspects of psychological research as well as data science research. So understanding it is actually beneficial for us in the long run, as well as the whole concept of experimental design. Experimental design really applies to every aspect of science. You have a manipulated variable, you have laboratory environments that you simulate a scenario, or you have field studies where you observe. Those are all kinds of things that we might have in data science. For example, if I have a set of data, maybe I want to manipulate one variable and see how it changes the outcomes. If I change the screw every third Thursday instead of every sixth Thursday, does it improve the quality of the product coming down the conveyor belt, month over month with consistency? Those are the kinds of questions that we would, kind of insert into predictive models, as well as, kind of do some, unstructured learning against, right? So those are the kinds of questions we would ask. In experimental design, we have this concept of a third variable problem, which always comes up in data science as well, which is that those are extraneous variables that might actually influence the dependent variable without us really wanting it to, or without our ability to kind of like tease out which one is the independent variable and which one is the confounding variable. So like a good example might be, is age a factor in smokers getting lung cancer? Something that you might do to control an extraneous variable would be, for example, have smokers that don't stop smoking. How do they continue on? So the no condition, no treatment condition group. So your control group, as we like to call it, right? As well as randomizing people of different ages to both the groups, the control group and the treatment group. Another option is holding constant that variable. So only 35-year-olds are in our study. We're only studying 35-year-old smokers. And then another might be to match a white female 35-year-old in the control group and match a white 35-year-old female in the treatment group. So those are just ways that we control for variables in psychological studies, as well as those are the kinds of designs that we would do when we're doing our questions for our data models. So I did want to talk a little bit about emotions, but we're not going to spend a lot of time on it because it's really not pertinent to computers and how computers could take advantage of things that we know in psychology. When humans make decisions, it requires emotion. And that is shown by damage to the part of the brain that's responsible for emotion called the amygdala. In people who have had their amygdala either surgically, separated from the rest of the brain or damaged in some capacity, they lose the ability to actually make a decision. They can't decide what to eat for dinner. They can't decide what to wear because we actually rely heavily on our feelings about the decision, more so than any black and white fact about the decision. So that's really the only place that comes into play, I feel, as well as memories are tied to emotions. And so if you're in an emotional state of sadness, you remember other sad times more so than you remember happy times, as well as learning can be state dependent as well. So that's another concern for humans, but not so much for machines. If machines are, for scoring, then that's a point for machine learning over humans. And again, one thing I do want to point out is that memories are tagged with emotion. And so that can actually make retrieval much, much faster. Like in SQL Server, we have, indexes, and we create an index on a certain attribute, and we can find that row faster because it actually has an index on a certain column with a fairly unique value. We can retrieve it faster. And emotions do that for our memories as well. So one of the tricks in the memory Olympics is to create really intense emotional reactions as you're memorizing something. So if you want to remember a deck of cards, you picture your late deceased grandmother holding the deck of cards or something like that. So you create this emotional tag basically, and those are called retrieval cues. Okay, so next we're going to talk about perception. Perception is a huge area, and I think it has a huge overlap. I am going fast, so please, if you have any questions, pop in. There's so much to cover in perception when it comes to artificial intelligence, because areas of artificial intelligence include how we perceive, vision, right? How we make sense of images, how we handle face recognition. Those kinds of things are all part of the aspect of psychology called perception. And so to really understand it from a biological perspective, you talk to the eye doctor, but to understand it from a, how do we interpret the images we see, we really actually need to look at the history of psychology and perception. So there's actually a lot of documentation on all of the failures of our perception and our ability to perceive. We have something called sensory adaptation. Machines don't have that problem. So a sensory adaptation would be like, I put these itchy socks on, but after 5 or 10 minutes, I forget about them and I go about my day like normal. A corollary might be we have a sensor that wakes up, it gathers data for a couple of minutes, and then it goes back to sleep when it realizes it's not needed. An example of that is Alexa. Hopefully I didn't turn it on for anybody who has that at home, but it is always listening for its name. When it hears it, it keeps that recording and it goes into action. If it does not hear its name, it discards the recording and then it goes back to sleep. Back to sleep. But so that's a very specific AI, instantiation of this idea of kind of sensing for a short period of time and then letting it go, because to continue to maintain an observation of that sensation would be absolutely overwhelming. And this is where you get into a lot of the kind of concerns with sensory, sensory disorders, or people on the autism spectrum, those kinds of things, where they just cannot get to a place of sensory adaptation for tags or seams in their socks, that kind of thing. Another problem with humans' perception is selective attention. We cannot possibly process all the data that we're getting at any given time. So we have to be very selective and discard things that are actually not very useful. And by useful, in psychology, it's based on the evolutionary biology kind of things of, is it going to eat me? Can I eat it? So things that invoke survival have a lot of our attention, whereas things that are just kind of background noise, we generally tune out. And there is another phenomenon called change blindness. And change blindness is where humans are actually fairly bad at visually changing perceiving changes in the environment that are relatively minor. So all of those are ways that machine learning are like more advantageous than humans. However, everything that we do with the eye happens in fractions of seconds. So same for most of our senses. There are some exceptions with like the sensations in the feet and things like that, especially in giraffes because they've got a long way to go. But for the most part, the amount of processing that happens is quite astounding. When we visualize something, we actually break it into subcategories of like size and orientation and things like that. And what they've discovered from some brain damage studies is that if you lose the ability to see an object, you might still be able to see the orientation of the object. Even if you cannot see it or identify it, tell you what it is, you might be able to say it's pointing left or right, that type of thing, because that information gets to a different area of the visual cortex, and the visual cortex processes that, even though you're not cognitively aware of it. Once it's brought to your attention, you can actually give the correct answer if you have brain damage in specific areas. There are two concepts in psychology that are interesting from the perspective of data science, because in my opinion, we only do one of them in data science right now, and that is in artificial intelligence, right? So top-down and bottom-up processing, and what those mean are, really in reference to, are we thinking about something and that affects our sensory input, or does the sensory input affect our thinking about a thing? And so humans can do bottom-up. Bottom-up is I felt it, and now I have a feeling or thought about it. Top down is I have a thought about it and it modifies my perception of that sensation. Really good example, if everybody's familiar with this one. You think you're going to go drink a nice Coca-Cola, and it's actually a glass of warm milk. right? You instantly have a totally different experience. If you knew it was going to be warm milk, you would not have had like a repulsion, right, reaction. So at this time, and I know there is research into all of this right now, there's not a lot of movement in robots or, sensory input that that drives thoughts and feelings in, or I will say thoughts in artificial intelligence. The problem is that we have to tell it how to interpret any sensation. And once we get to a point where artificial intelligence can have a sensation that is not pre-programmed or whatever, and then learn from it and experience cognition about it, then we'll be able to say that that AI is experiencing a bottom-up processing. So I find that super interesting when you start talking about, AI and robots and cognition and things like that. Humans win in the sensory aspect of things. There is a school of psychology called Gestalt. I hope I'm pronouncing that right. It's a German school of psychology. And basically, they have a lot to say about perception. And they have what are called the principles of perceptual organization. Some of those principles are things are figure or ground, like it's a figure like a person, or it's a horizontal plane that looks, at the distance like ground versus air, So those are ways that we kind of divide and categorize what we perceive visually. In addition, we also group things by proximity, similarity, continuity, connectedness, and closure. And those have really fun names. It's like the principle of good organization or something like that, of good continuation, the principle of good continuation. And what that means is that objects that overlap continue behind the overlap. So, I'm hiding my hand. No one thinks that my hand ends here and then restarts here, right? So our visual cortex and our perception give us that built in by default. Whereas in machine learning, artificial intelligence, we have to program that. We have to tell it to do that. Currently, the theory is that these things evolved over, many, many tens of thousands of years as part of our evolutionary biology. In addition to that, we have retinal disparity, which gives us the ability to have depth perception and how things are sized, how far away things are from us, those kinds of things. So obviously with artificial intelligence and, creating perception within robots, there are ways to mimic those things, as well. We still will always have, until we can get to the point where deep learning is happening, that bottom up stuff is the realm of humans and animals. So any questions here? Let me check chat. Nope, I don't see anything. Anybody got any questions? Okay, so memory is learning persisted over time. Memory and computer memory, lots of analogies to be made there. We talk about storing and encoding and retrieval as being the three steps of the memory process. This is analogous to our I/O, in computer terms. We have different types of encoding. There is actually automatic encoding and effortful encoding. So effortful encoding is everything I did to learn this stuff. I had to go read a book. I had to go listen to lectures, it took memorization and it took committing things to memory. Automatic encoding would be something like on a data row in SQL Server, we've got some columns that pre-populate anytime you insert a row. They've got default constraints, get date, maybe it's got the user who's doing the insert, user ID of the insert, maybe it's got some other things, but those usually fall into categories of like temporal, frequency, and spatial, right? So, GPS code location of, where the user is who is inserting that row, something like that. Our brain does that automatically, and we're not aware of it. We do it, but we're not aware of it. And some people are better at it than others. Some people have a better sense of time or space than others, and those cues are used for retrieval. So think of your cousin who can't read a map to save their life. They might not be as great with the spatial encoding as you are, something like that. So in addition to the parts of the memory process, we also have the types of memories, and there are two general categories of memories: implicit and explicit. Implicit memories include procedural, priming, and classical conditioning, and explicit includes episodic, semantic, sensory, and a couple of others. So why this is important is because we can actually steal some of this stuff when we start talking about natural language processing, or using data science features in order to understand how to motivate individuals to buy what we want them to buy, or change the behavior in the way that we want to change it for whatever reason. For example, let's talk about procedural. Procedural is actually like riding a bike, right? It's simple as riding a bike. Once you learn, you never forget how to ride a bike. Or there's studies of people who have had strokes and they can play the violin perfectly, but they couldn't explain to you how they're doing it. They have the muscle memory, and the motor neurons are still intact that handle that part of behavior. So this can actually also be cognitive, which is where data science kind of comes in. There are aspects of natural language processing that we learn automatically, and they're procedural, and we don't even know that we've learned them. One of them is actually called statistical learning. Statistical learning, which is not as cool as I thought it was, is when you understand the probability that exists in your native language of one sound following another sound. And there's lots of examples for this. I'm not gonna try to quote any of them because there's just so many of them. But if you have a situation where a native speaker hears a first syllable, they know the probability of which words will actually finish the sentence or finish the word because of that statistical learning. And they know it inherently, though they cannot actually explain it to you. And what they found is that babies learn this within the first year of life, usually by 9 months for their native tongue. So that's super interesting, and you wouldn't actually know that you knew it. Another example is this is a good one. The Royal Order of Adjectives. Does anybody know what the Royal Order of Adjectives is? Let me see. Anybody raise your hand out there? No one. Nobody. Okay. So the Royal Order of Adjectives is, we say 3 small gray kittens. We would never say gray 3 small kittens. It hurts, like it physically hurts to say it that way. You know the rules, you just don't know you know the rules, right? It's never really been sat down and explained to you in your native language, whatever that is. In English, it's the Royal Order of Adjectives, and it's out there. It's in my resources. You can look it up. Can we use that? Yes, absolutely. We can totally use that. That would be something that would indicate a native speaker versus a non-native speaker, right off the bat in natural language processing. Another example, which is slightly different, is that in the development of learning, and we'll talk about this a little bit more later, is this concept that we hit certain language stages in a very specific order, regardless of our age. And so an example is that a toddler will say "I going" instead of like "I am going." And English as a second language students learn that or make that mistake consistently before they move on to the "I am going." And so it's a very telling sign about where somebody is in their language development. So that's something that I think is super beneficial to know and use when you are, creating your natural language processing algorithms. So classical conditioning, this is Pavlov. Everybody's heard of Pavlov, right? Anybody not hear of Pavlov? Pavlov's dog. This is the, ring the bell and the dog starts salivating. We are not going to really go too much into that because classical conditioning is only ever about involuntary behaviors. And I cannot think of an application in AI or machine learning. If you can, please definitely raise your hand and give it a shout, because that would be fascinating to me. Episodic memory is events that have happened in your past. Last Thursday, we had lunch and you spilled the soup. That kind of a memory is called an episodic memory. Semantic memories are facts, such as Florida gets more hurricanes than Idaho. And then you actually have sensory memories, which are visual, auditory, olfactory, that kind of thing. And this is also related to tagging. And the way we actually store memories is in a huge network of, part of it includes all these tagged areas of, were you running when you heard the news that, Michael Jackson died? And, you remember what the birds sounded like, and like all of those different things tie in to create that memory network. Okay, any questions? Memory has two types of storage. I'm actually not going to go through all of this because I'm running out of time, and the cognitive part is the most interesting part of this. Just to say that sensory memory is a fraction of a second, although you do have an echo of auditory sounds for 3 to 4 seconds, which is rather interesting, I think. Short-term memory lasts only 15 to 20 seconds, and you can only store 5 to 7 to 9-ish items at any one time without doing any trickery like mnemonics or what they call chunking things into, like a telephone number has the area code and then the prefix and then the last 4 digits. That's how we remember phone numbers as much as we do. One of the things I do want to point out here that is very important for long-term memory is that memories can actually be corrupted. And this is a very interesting area of research that's happening about how when we extract a memory from long-term storage and put it into working memory, we reconsolidate that memory and put it back in long-term storage. And that can actually corrupt that memory for us. Memory is actually incredibly fragile and volatile. So as much as I'd like to say it, machines have us on that one. Learning. I like learning because one of the things that they use to define learning is that behavior has changed. And I find that interesting. So you can know a thing, but unless you actually do something differently or something different happens, it's not considered that you have learned it. So a really good example is how many people, went to driving school and they know they're supposed to use their turn signal and they still don't consistently use their turn signal. I'm guilty of this. What's interesting about learning is that it really kind of came into popularity in the psychological community during this period of behaviorism. And so Freud was Freud, but then the behaviorists got involved and everything became about, it has to be observable. It has to be an observable behavior. Your blood pressure is an observable behavior. It's not in your control, but it is an observable behavior. So it's an involuntary observable behavior. Changing your diet because you want to eat healthy, or driving slower, than the speed limit. Things like that you change your own behavior because you have read something or heard something, or you hear the sirens behind you and you think the cop's pulling you over. Those are learning examples. Another aspect of that is that it's not really considered to have taken place until it's a fairly permanent change in behavior. So you do it once or twice, it doesn't count. Classical conditioning, again, we're not going to talk about that because I can't think of any AI or ML applications, but operant conditioning is 100% machine learning. Like this is how we talk about machine learning. We give the reinforcement, like this is something that we provide, right? But it is still us providing this reinforcement. And the concept is that behavior that is rewarded, or what we call reinforced, is repeated. And there are two ways to reinforce a behavior. We either take away something that is aversive, or we give something that is pleasurable. Machines don't care about aversive or pleasurable, but we give them goals. Like we want this to be higher or we want this to be lower, so we steer its behavior based on that. When we do operant conditioning, there's something important called shaping. Shaping is where you break down a behavior into sub-behaviors. Let's say you're trying to teach a dog a trick, and you break it down into, well, first I want them in this position. I want them sitting first. So you first have to teach them to sit. Well, is there any sub-routine of sitting that we actually need to work on first? Well, I need them to look at me first. Okay, well, let's get them to look at you first. And so you shape the behavior over time. We do the exact same thing with our models, the exact same thing. So does anybody have any examples of models they're working on right now? And we can talk about breaking it out. Nope. So a good example might be, we want to predict, what the repair schedule, the perfect repair schedule might be for something. We would break out the little parts that make up what a repair schedule is, and each subpart is trained individually, and then it's the entire behavior might be trained to get the full model, something like that. Does that make sense, everybody? Make sure we got people so quiet. I guess it's lunchtime, everybody's eating. One of the fascinating things I find about humans and operant conditioning is this concept, and actually animals as well, reward schedules. And we don't have to worry about this as much for machines because it's just not a concern. We tell the machines what to do and when, and so we don't have this concern. But a reward schedule has to do with how the behavior is reinforced. Is it reinforced every time? That's continuous reinforcement. Is it only reinforced intermittently, or called partial reinforcement? Partial reinforcement is addictive. It is an absolutely addictive thing for humans and rats. So if you have a person who likes the slot machines, that's the perfect example. A slot machine gives you the jackpot intermittently, and that reward creates a lot of dopamine because it is intermittent. We don't know when that's going to happen, but once it happens, we just are flooded with dopamine, and we're very excited about it. And so we are willing to keep trying and until that next hit comes in. Whereas continuous reinforcement, it actually dies off real quick. And that die off of behavior is called extinction. We extinguish the behavior, right? After it's no longer reinforced. So to kind of come back to memory a little bit, one of the things that they've found is if we work on remembering something by practice, by repetition, over time, one of the things they found is that this concept of the forgetting curve, humans have a real steep drop off when they stop repeating something, where they begin to forget, and you forget a large portion of it. It can be like 70 to 80% within the first couple of days. And then that plateaus over time, and you'll retain it pretty much indefinitely, with some variations, if you die, things like that. But machines don't have that problem, right? Unless you've got hardware issues or other issues, right? We retain that memory indefinitely. And so humans kind of lose a point there from that perspective, because we have that extinction problem, we have that extinguishing problem, where if we're not continually reinforcing, if we're not continually rehearsing a behavior, we will forget it. We will forget about it. And that comes into play with this concept of spaced repetition. Well, spaced repetition is actually very useful And applications like Duolingo, and I can't remember the name of the other one. It starts with an A, Anki Deck. They use spaced repetition to help learning, to help teaching any concepts. Duolingo obviously is language, but the concept is basically if you get it right, then they wait 2 or 3 days and they show it to you again. If you get it right again, they wait 7 days and show it to you again. And if you get it right in 7 days, they wait 21 days and they give it to you again. If you get it wrong, it goes back into the deck and you might get it 5 minutes later, you might get it 10 minutes later, or you might get it tomorrow. But it's that idea that if you remember, if you're able to retrieve something from memory right on the cusp of forgetting it, you're able to retain it longer. And there's a lot of reasons for that in the human brain, and how we are more stimulated by a pattern that doesn't match the pattern, or an instance that doesn't match the pattern, and we create more dopamine for ourselves. This is helpful because then we can notice, the saber-toothed tiger in the bush, on the savannah, and we can get out of there, So we are pretty good at anomaly detection in certain cases. And in this case, what happens is by getting to that edge of almost forgetting, we create additional friction in the remembering. Machine learning doesn't really have anything to do with that. And that's actually a super benefit to using it there. Observational learning, I find this interesting because it's actually other people modeling behavior we want to learn. So, teacher shows you how to do a math problem, then you do the math problem. But also we learn, automatically, and we don't realize it as well. And that's part of that natural language processing that we pick up the royal order of adjectives, and we don't realize we have. What I like to do here is point out this thing called the adjacent possible. It's a concept that they talk about in science, which is right on the edge of everything we know is this border of things that we could know. And so when we increase our knowledge, we increase our surface area with that adjacent possible. That, I think, is a very good concept to bring into machine learning, because the more things that we are able to capture in our model, obviously there's overhead, obviously, there's limitations, then the more we can actually predict and know in the future. A lot of stuff is useless. I do acknowledge that. But it also, every time we increase into that adjacent possible, our adjacent possible moves out into that future unknown knowledge. And a lot of this has to do with how things are measured and blah, blah, blah. But there's also this other concept, which is called the zone of proximal development. And the zone of proximal development has to do with who's around you and who you can learn from. And an example of that is if we had, children and we just put them out in a field, they'd probably learn some things from each other, probably a lot of 4-letter words and bad habits and other things, but they would level off and everybody would kind of plateau at level of observational and experiential learning. What you then have to have is another person come in, a teacher, a parent, or somebody who has more knowledge and increase that zone of proximal development. And that's important because from the machine learning perspective, other models could actually train other models. That's the takeaway there. Any questions? Okay. Motivation, very quick on motivation. Computers don't need it, which is great. We don't have to bribe them. We don't have to give them doggy treats, none of that. They don't self-sabotage and they don't procrastinate because they're overwhelmed or fear failure. They are, however, totally influenced by the programmers and the people who build the models. So we have to be cognizant of our motivations and why we do things and have some self-awareness, or we need to have checks and balances of our motivations within our system of development. There is a concept of avoidance versus seeking. when it comes to motivation, and it has to do with that operant conditioning, right? So we either try to avoid being punished, which actually is not a reinforcement as you would consider it, or we actually seek pleasure. And again, models don't care about this. They do care about weights of things that we actually start them out on, right? So if we give something a higher weight than something else, we've created this pleasure or punishment kind of avoid or seek scenario. So like here's a couple thought questions, like what kind of things could we introduce to have data scientists avoid racial bias in their models? Would it be take away their money or give them more money for having caught a bias? My puppy's playing with her chew toy, sorry. So those I think are super interesting questions, and could we use them on the programmers and on the data modelers and the data engineers to kind of correct for some of these scenarios. Let's get into cognition. This is the meat and potatoes. Cognitive psychology is an internal process. It is a very new aspect of psychology or field of psychology because, as I said, the behaviorists reigned for many years. And a big part of that was that what happened inside the brain was not measurable. We only could resort to a person's observations, and people are biased, and we'll talk about that in a minute. And they have perception issues, and they have like all these flaws, you know, we're wonderful, flawed humans, right? Cognitive psychology is focused on kind of how we learn, how we think, how we decide, how we predict, how we weigh our decisions, all of those things. It's very applicable in artificial intelligence and in machine learning. And so if I were to give you any homework, it would be go dig into this area of psychology, because that is where the gold is going to be for you guys. In the 50s, we were coming kind of into the dawn of computer science, really 50s and 60s, and psychologists were picking up on this. And at that time, this new information processing approach theory entered into psychological research. It drew a lot of parallels between computers and humans, including using flow diagrams, computer flow diagrams, to diagram how thought processes played out in humans. And in addition to that, in I think 56, they held the first ever conference on artificial intelligence. And that was very, very interesting. One of the concepts or one of the aspects of cognition or cognitive psychology is how humans conceptualize and categorize knowledge. Any object, any information, any observation, any experience. What do we do with it, and how do we categorize that? There is an entire library of machine learning dedicated to categorization. Like there are so many actually. To know how humans do it and how the different fields in psychology kind of view it is super helpful. There are different approaches to this. We do this in other areas as well. There's the scientific taxonomy of like flora and fauna, and this species and that genus and that type of thing. In addition to that, there's a behavioral approach, of course, because the behaviorists ruled for so long. There's a physiological approach, like what is actually happening in the neurons. And some approaches that kind of went by the wayside were definition and family resemblance. And those can teach us a lot by their failures. Definitions failed because what happens to the corner cases? Let's talk about birds. Let's say I want to define a bird as something that has wings and a beak and feathers and flies, right? I'm sure everybody here can think of a bird that does not meet that definition. So we had to kind of not discard, but really kind of take what was good about the definition approach and discard what was bad about it. And that led to this family resemblance. And the family resemblance was, okay, well, most of it fits, into this category. And we focus on their similarities. There's another one that talks about prototypes. The prototype approach is like, this is the, absolutely generic, has all the qualities, of a bird. And then you might have, sorry, my dogs are going crazy because the FedEx guy just arrived, I think. So we have these kind of past theories until about the 50s when they started talking about this thing called the semantic network approach. And the reason that was introduced was because of how they were able to view neurons in the brain lighting up when different categorized images were viewed. And so it kind of created this mental map on the neural imaging. There were some benefits and some drawbacks of that. And so a new version was called the connectivist approach. So connectivism is the actual word. And that we train our network of categorization by sending activity down that network. And so you have this idea of a concept like a canary. And this is the image I borrowed from Goldstein, I think. Yes, Goldstein. And so the semantic network had this concept of input units, output units, and hidden units. So the input would be sensory, the output would be like a behavior or a thought, that kind of thing. So we see a canary, we see its representation. There's some hidden things that go along. We see that it grows, we see that it moves, we see that it flies, we see that it can sing, right? These are the attributes of it. And then we have, the relation. It can fly, it can sing, it can grow, and it can move. I am so sorry about the dogs. So just real quick, error signals, is it tall? No, it's not tall. So the error signals go back propagate. Does this ring any bells to anybody? This is 100% machine learning, neural networks right here. And this is a concept that grew in parallel kind of with the concepts of machine learning and neural networks as the different mathematics and psychology and computer science fields got together in these conferences. So I find that super fascinating. I am so sorry, I'm running out of time. Problem solving. We have this Gestalt approach is basically we have to have a proper mental representation in order to solve the problem. There are two types of problems, insight and non-insight. Insights are sudden. We oh gosh, I see a problem because I restructured it. That's what the Gestalt psychologists call it. If you look at it from a different view or that type of thing. Insight problems actually come out of what's called the default mode network, which is when our brains are kind of daydreaming, or we're taking a walk, or we're taking a shower, or we're taking a nap. Executive control network is where we're actually super focused on a problem. Those are non-insight problems. Those are methodical and they're gradual progress towards things. We have barriers to insight problems, and that's a function fixedness. And that means, the saying, if you only have a hammer in your toolbox, every problem is a nail. That's function fixedness. If you have a hammer, you could actually use it as a weight. You could use it as, a pendulum. You could use it as a pry bar. There are other uses for a hammer than as, a hammer. But that is a barrier because people will get stuck on something. And that becomes a problem when we're building models. Let's see, there are some other things. Let's talk about heuristics and biases super quick. Heuristics are shortcuts for making decisions. And we use a lot of bias in that. And that's part of the fast approach to making decisions. So definitely I have way too much to cover for here. There's also the information processing approach to problem solving, which is generating the problem space and defining the initial state, the goal state, the doing the analysis of how to get there, including subgoals, and then doing operations to get to the subgoal. Okay, so using analogies to problem solve. There are three aspects of that: noticing, mapping, and applying. We can actually use a lot of this in machine learning if we can, for example, borrow parts of one model to use in another part of a model that is a totally different area. Basically, we have stored procedures and functions. You know, we modularize our code, you know, because things are analogous. There are lots of applications in AI and machine learning as well. We just need to really get to the point where in deep learning, for example, things can go seek out different algorithms by itself. Meta-cognition is the idea that we think about what we're thinking. And that is supposedly only by humans right now. I don't know that that's true, but we can't test it because it's unmeasurable right now. Gosh, we're at time. Mala, do you want me to keep going or do you want me to wrap up? You're on mute, Mala, or Kathy. Mala?
Sorry, I just got into another window and I could not get back. No, we are almost done. I can give you another 3 minutes if you want to summarize what you talked about and then wind up. That would be excellent.
Okay. So cognitive biases. Bias is a form of heuristics. We have a ton of them. Let me actually, well, there's a website at the end with all the list of, it's a Wikipedia article with all the list of cognitive biases. It's huge. Go read it. You'll be shocked. And you have them. I have them. We all have them. The thing to understand is that they're there and we have to control for them. That's the important thing. Let's talk about ethics super briefly. The one thing I do want to say about ethics and psychology is that psychology is very careful about the human impact and the animal impact of research. And I don't see that in data science. I don't see that in machine learning. I don't see that in artificial intelligence because there is no oversight. There is no, like we have committees. Every research institute has a committee that will approve or, you know, just reject research if it has human or animal participants or subject matters. And so I think that something like that is important because, for example, and I don't know how true this is right now, but my understanding is that some navigation apps will steer you around a traffic jam, but periodically they will send a person into the traffic jam in order to test if that's still a traffic jam, you know, if there's still that bottleneck. And this may not be the case anymore. It may have been the case 10 years ago. I don't know. But to me, that's unethical, right? It may be in the end user license agreement. I don't know. But sorry, puppy scratching. Informed consent is a big aspect of participation in research studies, and I think we really actually need to look at that and map towards that. This is the tip of the iceberg. I can't even begin. If you didn't find this fascinating, blame me, because this is fascinating. I didn't present it properly because there's just too much. I had pages and pages and pages of stuff to tell you about, and this was just all I could fit into an hour, and I didn't even do it that well. So definitely go research more if any aspect of this is interesting to you. If it's not, again, go research it anyway, because it's probably my fault. Any questions?
Any last minute questions, people?
Thank you all for your time. I appreciate it. Sorry about all the noise in the background. I think that Cindy's right. It's very helpful, not only in how to deal with each other, but also really, if you're going to pretend to be human, you know, as a machine, you need to understand how humans function. So. Thanks for coming. I very much appreciate it. Hope you enjoyed it. Definitely send me feedback because I need to get better.